from different organizations, including one of our speakers who works for IBM in the industry. But we're not going to promote any products related to those groups. We're really just going to talk generally speaking, but that's our obligatory disclosure. And then your tutorial organizers. So first, myself, I'm David Gotts. I'm from the UNC Chapel Hill. I'm also affiliated with the Carolina Health Informatics program, where I'm the assistant director. I'll also introduce, let my fellow tutorial speakers introduce themselves.
Jesus Caban, I'll be the second speaker.
From Walter Reed.
Oh yes, I'm Jesus Caban from Walter Reed, from the DoD. I'll be the second speaker and also the co-chair of the working group.
And hi, I'm Adam Parrott from IBM G.J. Watson Research, and I'll be the third session giving a little hands-on tutorial about how we can actually build some of the visualizations that you'll hear about in the beginning. And that will be a
Can't hear you.
Not a very interesting opening statement. I was just saying my name is Adam Parrott from IBM Research, and on part 3, I'll be helping give an example of actually a hands-on tutorial of how you can build some visualizations. And this will be assisted by Yoshi Krause of NYU, who will be arriving shortly.
All right, so that's your team of tutorial organizers. The agenda for today. So we are going to split the tutorial into 3 high-level sections. I will start with session 1, where I'll give a brief introduction. That's this welcome that we're doing now, as well as an introduction to visual analytics in general, and some of the underlying principles that will help us move into the next 2 sessions. The second session will focus more on application domains, specifically applications of visualization and analytics to healthcare, and we'll look at different kinds of visualizations and some places where it's really been applied in different types of use cases. And then finally, session 3 will be more of a hands-on exercise, as Adam hinted at before, where we'll really get into the lower level technical details using a particular toolkit, and we'll see some examples and build up into a higher level system that's open source that you can actually go out and see how the baby steps we can take in the limited amount of time we have can then build into a much larger, richer visualization-based application. So just in terms of difficulty and accessibility of the material, the first section will be really pretty basic, accessible to everyone. The second section will be perhaps a little bit more advanced, but still focused largely at a general audience, and will be pretty accessible. The third session, where we're getting hands-on and detailed into code and things, we're going to see real source code and some programming. So it'll be a much more technical discussion, and then we'll wrap up at the end. All right, so that gives you a highlight. The one thing I'll mention is at 10 o'clock we will take a break for 30 minutes, which aligns with the broader AMIA break, so you can get coffee, get caffeine, and be ready to come back and type some code. All right. So that's our agenda. The workshop, the tutorial that we're presenting here today is really part of a broader context of visual analytics in healthcare. And just to set the stage for that, I want to point out a few things. First of all, we've seen this growing electronification of data, and meaningful use and incentives to go out and deploy EHR systems and all sorts of other systems that gather electronic data. So now we have big piles of information that before might have been in paper. Now they're in a computer, and we can start to learn from that data in different ways. We also have things like clinical data networks, such as PCORNet, where we're going out now and connecting a lot of these systems together to get broader populations across multiple institutions, where we can do even more interesting things by looking at the data. And then there's a precision medicine initiative, where we're getting more data, we're getting genomic information, we're connecting that with EHRs and trying to inform the best decision that people might make. So as we're gathering more and more data, applying more and more analytics, it starts to become important to think about how we can then present that information and allow people to interact with it in such a way that they can start to make decisions informed by the data. And if we just present our data in a bunch of tables, as I'll show in a minute, it's going to be harder to do the kinds of things that we need to be able to do. So there's been a growing emphasis on visual analytics in healthcare. This was evidenced in March of this year, where JAMIA had a special section focused specifically on this topic. The title, the cover page focused on one particular article outlining the research opportunities and challenges. But within that issue, there was a survey of papers in this area. There were a bunch of other use cases and other research reports. So I encourage you to go out and look at that if you haven't. I think it's a good sampling of a set of things that are taking place right now. At the same time, there was an effort underway to establish AMIA's newest working group, which was officially launched over the summer, which is the Visual Analytics Working Group. That's the host of this particular tutorial. And I encourage all of you, if you're interested in this topic, to go ahead and sign up. If you're an AMIA member, it's free. If you're not part of the working groups, you just go to the website and you can sign up. We have a community, a mailing list where you'll get announcements about different kinds of things, share resources. So I encourage you to do that. If you're not an AMIA member, then first of all, become an AMIA member, then you can sign up for the working group. If you are hesitant or while you're waiting to do that process, there's also a website, visualanalytichealthcare.org, which has been around for before the official working group started. And there's a bunch of resources there, as well as a mailing list that's been around for a while that you can join. And many of the announcements end up going to both places. All right. Now, in addition to the tutorial, some other synergistic activities have been taking place. That includes a set of workshops. So the 6th annual Visual Analytics and Healthcare Workshop took place just a couple weeks ago in Chicago. That was co-located with IEEE-Viz, which is the premier visualization conference, agnostic to healthcare, it's all domains. And it's the place where the best work goes. So the papers that are published there are journal papers, so people send their best work there. So it's a great venue if you are, again, interested in this topic and learning more and diving in deep. That's a really good place to go. The papers from this year's workshop are archived on the ACM Digital Library, and demos, posters, and other material either are on the Visual Analytics Healthcare website or will be shortly. All right. And just a little more about that. This workshop was actually at AMIA last year, so some of you may have participated in that. As I mentioned, it's the 6th annual one. It started at IEEE-Viz for a few years and went to AMIA for a couple years and back to Viz. Our plan is hopefully to try and bring it back here next year and to continue to go back and forth with the hope of bridging across these communities where we have the AMIA community that has a whole bunch of data, complicated analytics that we're developing, and a bunch of use cases where people have to make sense out of that data to make informed decisions. And then we have another community that spent a long time focusing on ways to visually present and interact with that data to help make better decisions. And by bringing these together, we hope we can make a difference. All right, so the last slide before we dive into the real material is, again, encouraging you to get involved. A vibrant community like this, the working group, which is new, needs your interaction and support. So please come participate in events like this. Help us generate ideas, tell us what might be useful, and donate your time if you're interested. We'd love to have help in organizing these kinds of things. So join the Viz working group. Also stop by the Viz working group meeting. We'll have our first ever working group meeting tomorrow. That's at 8 p.m. in Franciscan D. So I encourage you to come. And then finally, contact any of us up here on the stage. We're all involved in the leadership of the working group, and we'd love to have more people coming on. All right, so with that, welcome. Let's dive into the actual material here for the introduction, where we're going to focus on what is this topic. Yes, for people in the back, there are tables in the front. You may have to fight through people. The arrangement here is not the best, but there is plenty of seating in the front. All right, so let's talk about what is visual analytics, why should we use it, and what should we know in order to use it effectively. And I'd like to start that by looking at an example, and let's take a bit of a test. Okay? So here's a table of data, which should look familiar to most of us. We often look at tables like this and try and make sense out of things. This one is a summary of sales data for 3 years by 4 different regions and broken down into quarters. Okay, so we have 4 quarters each year. So what I'd like to do is ask you to look at this table and raise your hand when you answer my question, which is, which quarter and which region has the highest sales figure?
East 20.
Okay, so I see some hands coming up. It's going fairly quick. All right. You probably looked at the table, started scanning in columns, looking for the highest first digit, and maybe you finally saw that 87,000. That's pretty big numbers there. Okay, and some of you may have missed it. All right, so let's do something a little bit harder. Let's look for the top 3. The bottom 3. So raise your hand when you have this. Okay, some hands are going up. Slower this time, right? It's more work. Now, not only do you have to just scan and remember the highest number, you have to think about the first highest, and second highest, and third highest, and do a lot of different comparisons. It takes a lot more mental energy to try and do that task. Okay? So now I'm going to make one more change. And I think here, if we try and do the top 3 and bottom 3, if you raise your hand when you find it, it'll probably be a lot faster, right? So now you're able to do this much more complicated task, top 3 and bottom 3, much faster than you did even just finding the highest sales figure. So we've now used visualization to successfully solve a task much more quickly than we could just by looking at the tables. Okay, so with that introduction, let's go into the definition of visualization. So what do we mean by visualization? And we can think about this pretty broadly. It's just the communication of information using graphical representations. So that means a table, like we just saw, is a visualization. We have a nice structure that lets us look up, in 2012, the second quarter sales for the East region pretty quickly because of how we're organizing things spatially within the table. If we add in the color coding that we saw before, now we can do a lot more tasks, also very quickly. Other visualizations that we're familiar with include maps, bar charts, pie charts, line charts. All these are pretty effective. They're very common because they're good at what they do. It helps us look at the data and understand it much more quickly than looking at the raw information. Now it's also important for us to note that because we have all these different types of visualization, how do we actually visualize our data? What's the best way to look at it? And it's important to remember that it's not just, here's the data, this is the best way to look at it. It depends on what kind of task you're trying to do. So the color coding that we have on the table is really good at identifying outliers, because we can see things that are really light or really dark. We can also look up values because of the structure of the table. But what it makes it hard for us to do is to look for things like trends. So how are sales evolving from 2011 to 2013? This view, we can try and think about it, but again, it requires us to dive into the numbers, put them into our brain, and try and understand how they're changing. Where if we have a view like this, we get a much better sense of what's happening. Now this makes it harder to see the top 3 and bottom 3 perhaps. Maybe the top 3 are okay because they're outliers towards the top. But it's really good for looking at what's happening over time, and we can see a slight decline perhaps, but it's pretty flat across all the regions. Similarly, if we wanted to know which quarter historically does better, whether it's the first quarter or the third quarter or the fourth quarter, right? This kind of view also makes it hard for us to see. And the first view makes it hard for us to see. So we can think of a different way of presenting the data. In this case, we plotted 4 columns, one for each quarter. And we have 12 samples for each quarter, right? Because we have 4 regions and 3 years, so that's 12 samples of quarter 1 sales. And I can plot them in the first column and do the same for each of the quarters. And I can see that quarter 1 has higher sales than quarter 3, which has typically the lowest sales. And so different views give us different insights about the data. So it's not just the data that tells us how best to present it, it's also what we want to learn from the data. Now from those basic building blocks of bars and lines and those kinds of things, which we'll talk about more, we can get to more complicated examples, such as these, which are all healthcare related. Now we have multiple views that are coordinated with each other, and we can really start to interact with the data and perform some complex analytical tasks. So with modern technology, we can do some really interesting things. But visualization isn't just about modern technology and data collection. So one of the earlier examples of healthcare-based visualization is from John Snow, and we'll see more examples of kind of the history of this a little bit later in the tutorial. But this is a pretty famous one from the 1850s, where John Snow, who's known as a father of modern epidemiology, was studying cholera outbreak in London, and ended up creating this map that you see here to show where people died from the cholera outbreak. And at the time, the leading hypothesis was that there was kind of bad air. It's just kind of spreading over the general region. John Snow created this map. If you look carefully, you'll see black regions next to the roads. Those are essentially little bar charts, where the height of each of those bars corresponds to the number of people that died at that address. And we can start to see that it's clustering around a region here. And at this resolution, you can't quite see it, but where that orange dot is a water pump that was contaminated. And this was able to help persuade them to shut down the pump. There's some debate about whether this really helped stop the outbreak or whether the outbreak was already kind of dying off before they reached this point. But it shows the visual communication ability of visualization allowed you to communicate pretty complex data that you capture across a population of people in order to help someone make a decision to shut down the plant. All right, so those are some examples of things that we can do. The question is, why does it work, right? Why is good visualization effective and allow us to see things that otherwise we have to spend this mental energy to try and understand out of the data? And what it comes down to is our eyes and our brain are really good at seeing patterns. Right? We perceive things and we can interpret them. We can look for patterns, we can look at trends, we can find outliers, and we can do all of that without cognitive effort. It's built into our human perception system. So what we'd like to do in visualization is try and leverage the things that our brain and our eyes are good at and come up with a way of presenting the data so that we can precognitively see the type of information that will help us answer our question. And so that requires us to understand how different ways of representing the data visually map to our ability to perceive. Now, if we're talking about the computer-based world, where we're not hand-drawing things, as in Jon Snow's example, then we need to think about how we're actually going to compute from our data this visual representation that we can work with. And so the canonical visualization pipeline, which is shown here, has a few different steps. You start with your raw data, you do some data analysis, perhaps some modeling, you might do some data integration, some other transformations, some cleaning. You eventually get to your prepared data. From your prepared data, you then apply some filters to narrow down to a set of data that you're interested in looking at. That gives you your focus data. You then need to do a mapping to map your focus data to some geometric representation, that graphical representation that you then want to put on the screen. That can then be rendered into an image that you see on your screen, and you have your final visualization. Now, historically, this has often been thought of as a bit of a one-way process where visualization is presentation. But as we get into visual analytics and you start interacting with your data more and more, there's also a feedback loop. That as the user looks at that image, now as they interact, you can change the parameters of your data analysis, or change the parameters of your filtering step, or the mapping step, or even the rendering, to change the way that your visualization looks based on your interaction, to help you look at the data in different ways to solve different tasks based on what you just found. And now you can support an analytical process. Now within this pipeline, the rendering step is largely a solved problem. In the web-based world, we have things like Canvas and SVG. There's also OpenGL, DirectX, Java 2D, a whole bunch of libraries that are out there for taking a geometric representation and putting it into an image. So we're not going to spend too much time on that. We typically use something that's a bit off the shelf. But when we're creating a visualization, our effort usually goes in those other steps: the analysis, the filtering, the mapping, and the interaction design. And so that's what we're going to talk about a lot more today. Now this pipeline, as I mentioned, is the visualization pipeline. Visual analytics as a field is a bit broader than that. What we really want to combine is this notion of mapping our raw data to a visual representation with a larger picture of how people solve problems and more sophisticated underlying mathematical modeling techniques, things like machine learning and classification and data mining and regression and all sorts of other statistical tools. And so that leads to this model of visual analytics, right, which combines data going to visualization and your model, they're linked together, and then this whole section on the right, which is how people actually make sense out of data, deriving insights that generate hypotheses, and then you interact to test those hypotheses that generate new insights. And you can see this as a much more iterative, cyclical process than the previous model. But that model we just looked at really fits well within this higher level representation. All right, so let's, for today, focus on this visualization pipeline part. And in particular, we're going to focus on the mapping stage. Right? Visualization and visual analytics are big topics. We only have a limited amount of time. So we're going to focus on a small topic that's going to give us some building blocks and some fundamentals that we can leverage later on. And so the mapping process is really important because this is where we decide for a given set of data, how are we going to represent it visually to exploit that human perception. And this happens after we've done our data analysis, after we've done our filtering. That's stuff that we can talk about at length another day. But we're going to focus on this step, which is often called visual encoding. Now the goal of visual encoding is to take your data, that's the prepared focused data after those other steps, represented by the blue here, and in some way map that to graphical representation on the screen, that used to be bars, such that that graphical representation that we have can be easily interpreted by the user who's looking at it. And that requires us to understand how people interpret those graphical marks to best get them to gain the insights. And so then our job as a visualization designer is first to think about what is that visual representation that conveys the insight that we need people to understand from our data. And then think about how we can define that mapping function in an algorithmic way to convert our data to geometry based on that design that we came up with. And that algorithmic part is really important because it's the thing that we don't want our design to be just a one-time design where we're handcrafting something. We want it to work not just for this data set, but for other data sets like it. Not just for one patient, but for all patients, for any individual patient. Not just for this population, but for any population. Not just for this cholera outbreak, but for any cholera outbreak. And that can be hard, right? We have to think about outliers, we have to think about edge cases, we have to think about the types of data we're dealing with and any prerequisites about transforming and the analysis and focus step. We also have to think about what will happen if we scale to larger volumes of information, how that visual design will work. And so all of this makes this mapping process challenging, but also fun. Right? It's like solving a puzzle. How can we solve this generally? All right, so let's talk about some of the building blocks that go into this mapping process. And what I'm going to talk about are 8 visual variables, which we can control during the mapping process. And this characterization of the things that we can control comes from this interactive data visualization book by Ward, Grinstein, and Kine. There are other ways to characterize this, and we'll see one example of that a little bit later. But the key is we just want to start thinking systematically about what are the different things that we can control in the mapping process. So the first thing is location. And we can think about things in one dimension of location. So in the beginning, I have a bit of a timeline here showing my family's age. I have 3 young kids and 2 adults who are pretty close to each other. And I have in one dimension a meaningful chart. We can also use 2D charts, scatter plots, or there's a map on the bottom left. That works pretty well. You can also use 3D, but that's rarely used. And part of the problem with 3D is if we're dealing with abstract data, right, then embedding that into a 3D space puts in all kinds of additional complications that our minds have kind of evolved to understand a 3D physical world that doesn't necessarily reflect what we're trying to draw. So if you're rendering a molecule or something that has a real 3D shape, then 3D can work pretty effectively. If we're taking abstract data, adding that 3rd dimension actually often makes things harder to interpret rather than easier. So, but it's done. Here's a 3D scatter plot that you can see at the bottom. That has another problem in addition to just being 3 dimensions, which sometimes makes it harder to see. It's also using a rainbow color map, which we'll talk about later on. All right, so that's location. The second visual variable is the notion of a mark, which is an atomic graphical primitive, often called a glyph or a symbol, and it is the shape of the thing that you draw. Okay? It's separate from the scale, its orientation, or its color, just the shape. So here you see a bunch of different marks. Each column is a different mark. You see circles, triangles, squares, independent of their orientation and color. Now those 2 things, position and mark, are the 2 basic variables that we need to set. We need to have something to draw and a place to draw it, and that gives us the building blocks for an initial chart, such as the scatter plot you see here. So already we can see something pretty informative. We have a relationship between age and height, and because we have 2 different marks, we can see there are those triangles, right? They're kind of lower than the circles. So there's something interesting about that group that we might want to learn about. All right, so position and marks. The next visual variable we have to control is size. We have in 1 dimension, that's length. In 2 dimensions, we have area. And in 3 dimensions, we have volume. We can control all of those with the caveat that our ability to perceive differences in those different sizes doesn't always work as you might expect. Okay? So if you look at this particular picture here, if you look at the blue dots, which one of those looks bigger? The bottom one, right? Bottom to the bottom right. And of course, they're both the same size, as I'm sure you probably have guessed. But the size, the way we interpret it, is impacted by the size of the things around it, its context. And so if we use shape and size to encode things in our visualization, that's going to affect our ability to make good judgments. So we'll talk about some things to improve that. But that's not our only flaw. Okay, here we have 2 shapes. Which one of those is longer? They're the same length. If you look, they're aligned on this diagonal edge on the left-hand side, and that essentially shifts the top one over to the left. They feel lined up, but they're not really. And so we see that A seems shorter, but it's not. These 2 tables, you may have guessed by now, they are the same shape. We've just rotated it. Okay. Our understanding of shape is impacted by that. And how about these 3 cars? Okay. Those are, believe it or not, the same size. And even when I tell myself that, I don't believe it. Because that third car really looks a lot bigger than the first one. So even if we're conscious about these kinds of effects, it's hard for us to overcome them. All right, so when we're using size to compare things and encode information, a few tips to try and avoid some of those problems. First of all, limit ourselves to smaller numbers of dimensions. We're better at length than area, and better at area than volume. And so we can compare the length of those lines more accurately than the area of the squares. And if we align our shapes so that there's a proper alignment along the left-hand side, we can more easily judge the length of those lines than if they're scattered about. Exact same values using length instead of brightness, and it's much easier for us to try and understand. The other thing that often happens in visualization is people try and get fancy and sort of gradients and other kinds of things. Now, if you're encoding your data with brightness on a scale where you have from kind of white to black, and now you start adding 3D stuff and color gradients, now we have two squares that in fact are the same color, right? But because of the gradient, they look different. The one on the left looks darker, but in fact, they're really the same color. So, something to be aware of. Now that's specifically brightness. That's just one part of the larger color variable, where we can set not just lightness, but also the hue and the saturation to change between different colors. And hue is basically the wavelength, what we often think of as color, and then saturation is how much of that color do we have versus gray. That gives us a color space that looks like this kind of cylinder where we can describe any different color. And there are lots of different color spaces that are out there. This one is perhaps most intuitive for us because of how bright it is, what color it is, and then how much of that color we have. But in fact, what we use in most technology, like software, is the RGB color space, where we describe color in terms of how much red, how much green, and how much blue. And that's because our screens have red pixels, green pixels, and blue pixels. And if you look really close, you can sometimes see them. And those add together to give us the colors we want. And if you have no red, no green, and no blue, it's just black. And if you have all of those things turned on all the way, you have white. And that's typically represented in this kind of triplet of numbers that go from 0 to 255, this kind of 8-bit color. There's a whole bunch of stuff we can talk about color. It's multiple lectures just on color, right? But what you might recognize if you've done any coding on the web is this hexadecimal notation on the bottom with the F's. And the FF is 255 in hexadecimal, which means all the way on. So it turned red, green, and blue all the way on. That gives us white. All right. So what we typically do in visualization is define a color map where we have a range of colors that we map from some range of values that we want to visualize into those range of colors. And those color maps can either be discrete or continuous. If we have continuous values, like a real number, we often use a gradient like you see at the top. If we have discrete values, then we can use a discrete color map, such as the one we see at the bottom. Or we can take a real value and actually discretize it and turn it into buckets, where we can use a discrete color map. Now there are different kinds of discrete color maps. The one on the bottom left is good for categorical values, because those colors are not perceptually ordered. It's hard to sort them from least to most, whereas the color map on the bottom right does have a natural ordering. So if you're going to have now ordinal values, then you want to use a color map like you have on the right. And so that is really what's wrong with that rainbow color map that I mentioned early on in the talk, is that the values in a rainbow color map are not easily ordered. Perceptually, it's hard for people to put them in a meaningful order. So it's often the default value in a lot of different source types of visualization tools, which is a problem. So you should try and avoid the rainbow color map in general. Okay? Lots of literature has pointed to that. Other things that you should be aware of is color blindness. And color blindness is quite common. 8% of men, roughly, have color blindness. It's not as common in women, but still there. And the good thing to do there often is to think about a safe palette, but if that's not possible, because that limits your choices, it limits what you can encode, then have options where you can change from one color palette to another. Okay? That overcomes that limitation. The other thing I'll point you to is something called colorbrewer2.org. So as I mentioned, color theory and kind of understanding how people perceive color is its own big field. Cynthia Brewer has a really good resource which is focused a lot on maps, but has a lot of good lessons for all visualization in terms of how best to use color. In fact, a lot of the color palettes that are suggested by Color Brewer are in the toolkit that we'll use in our hands-on exercise. So embedded within that is support for the Color Brewer color scales. All right, the next thing we have is orientation, where we can map the angle of our object to a particular value. Here's an example from the National Weather Service where they're encoding wind direction and speed. You can see the speed is this line chart, the height, and then the direction is encoded by the angle of this glyph, which is L-shaped. And so why L-shaped? Because if we just have a line, we lose our ability to distinguish between pointing one way versus the other. Okay? So we have to pay attention to symmetry. If you have something like a triangle or an L, you can rotate all the way around. And as you have more and more symmetric shapes, you lose your ability to encode something by rotation. The next visual variable is texture, and this is rarely used. Okay, this is used a lot in black and white kind of printing where you don't have color, but it's hard for us to interpret this. I want to mention it for completeness, but in general, this is rarely used. Okay. Then the last one that I want to mention is motion, where we can actually change any of the values of those other visual variables to achieve some effect. And so that's typically done with animation. And here you can see a couple of examples in motion. These are typically associated with some sort of interaction where a user has done something, and now the visualization is going to respond to that by changing those mappings that we just talked about. Or the data might be dynamic. If you're watching a static visualization where the data is changing, now all of a sudden the latest tweet came in, so your count of tweets has changed, so you can change the height of your bar by animating the height of your representation. Now, this is probably stealing your attention looking at these things dance around. And so that's one reason why you need to use this judiciously. Okay? Motion is really strong pull on our visual attention, so you want to use it judiciously. And use it primarily to focus on corresponding data points across transitions. So the top one that you see with the scatter plot matrix, user is selecting some dots in one view, and in response, dots are being illuminated in the other view, so that you can see the correspondence based on your user interaction. And you can see if the dots are over here in this two-dimensional space, well, that's where they are in the other two-dimensional space. The bottom view is showing you zooming in and zooming out. And often when you pan a visualization or zoom into another region, if you just make that change instantaneous, it's hard for your mind, you have to rebuild your mental map about where things are. By having things animate smoothly, you can understand where things are coming from and where their new position is. And so that's the reason to use animation. All right, so those are our 8 visual variables. And during mapping, we want to convert our attributes to those visual properties with some kind of algorithmic function. But we need to choose which ones to use. And as I've hinted at in a lot of the discussion here, they're not all equal. So there's a landmark study from Cleveland and McGill in the 80s that actually did user studies to try and understand how these different variables, how effective they are, and how well we can interpret them. And they characterize them a little bit different. You can see length and volume and area are 3 separate things that they tested instead of just size. But what they came up with is an ordering that looks like this, where you have position along a common scale first, so think of things like a scatter plot. Position along identical but not aligned scale, so you might have 2 scatter plots next to each other where you can compare across them. Then length, which is our one-dimensional size. Angle and slope, so think slope of lines or angles in a pie chart. And then below that you have things like area, and then even worse you have volume, those 3D representations. Right? Much harder for us to interpret. And then finally at the very bottom, color hues. It's hard for us to interpret color. Okay, so an example of some not so great visualization. was from a meeting I was at the NIH last week, and I had to take this snapshot because I knew I was coming here to talk about this. And here's a 3D pie chart, which puts perspective onto our view. So now the things on the back side are actually smaller than they should be, because it's tilted over. They use color gradients and stuff to make it look fancy, which is okay because we have categorical things, so it's not really introducing confusion, but it's not necessary. And then the pie chart uses angles, and there are a lot of little tiny slices that are almost impossible for us to compare. So if we just had a nice bar chart, horizontal bar chart, we'd have a much better summary of where NIH spends their money each year. All right, so that focuses primarily on individual marks, those 8 visual variables. But that's not all we care about, because a lot of what we do with visualization is looking across multiple marks and trying to understand patterns that are interpreted across them. We saw that with some of the illusions, right? The size of the circle depended on the size of the things next to it. And so related to that are this family of Gestalt laws, which tell us how we understand things across patterns. Okay? And we'll review each of these. So first, we have the notion of proximity. Okay? When we have multiple different data points, and they're put on the screen, the proximity between those different data points, how close they are to each other, end up telling us a lot about how we group them together in our mind. So if you look in A and B, what we have is a grid of data points that are almost identical. The only difference is that in A, they're shifted slightly closer together. Each kind of column is shifted slightly closer to its next column than the rows. And in B, the rows are slightly closer together than the columns. And now if you look at that, right, without even trying, you probably see in A a bunch of rows. And in B, you see a bunch of columns. And you start connecting mentally each of those dots into a group just because they're slightly closer together. And meanwhile, in C, we have these 2 clusters, right? You think of it right away as 2 groups of things because they're co-located next to each other. So proximity is a pretty strong effect. And what it tells us is when we're thinking about how to map our data values to those visual variables, we want to do that mapping in such a way that the marks we create for related information end up being positioned closer together if we want people to be able to interpret those groups without having to engage the mental machinery of starting to think about the value of things. Now that's just one kind of effect, right? This interplays with lots of other effects that are going on in our mind. And the next one is similarity. So before I created columns or rows by just shifting the location of dots that were all identical. Here we have dots that are different. So the first one, we've just changed the color. It's the same mark, but they're different colors. And by shifting those colors, again, mentally, you immediately start to group those into rows. Part B, you're doing the same thing, but now it's not a difference in color, it's a difference in shape, the difference in mark. And the X's and the circles end up being grouped together. So we want to use the similar graphics to define our rows, columns, or groups, whatever we want, however we want that information to appear. If we want people to connect these things as being related to each other, we should use the same kinds of visual appearance. And we saw that in the very beginning when I showed that scatter plot of fake data of height versus age, and we had those triangles, right? You would immediately start to group those triangles together because they were similar in their mark, and then you started to find that, oh, there's this group of them, they're all lower than the others. You were able to look at the circles versus triangles as groups rather than as individuals and compare their differences. In the same way that we could do that with the color on the table and not looking at the individual numbers. All right, so the next Gestalt law is the notion of connectedness. And it's actually not part of the original Gestalt principles, but it's very effective on how we group things. And those are connectors between our different elements. So if you look here, we have in A, dots that are closer to each other kind of horizontally, but they're connected by these vertical lines. And so you probably see 2 groups, one on the left, one on the right in A. That connector is overcoming the value of the proximity, where in the previous example, we had dots when they're closer together, we grouped them together. So here the line is stronger. Similarly, in B, we have differences in color. You can see that that connector tells you that they're related to each other, even more powerfully than the change in color. And the bottom two give us different shapes, different sizes. Okay? In all cases, those connectors work really powerfully. So, using connectors to link group marks, if we've done some analysis and we know that these things are linked to each other, is really powerful. That works really well. The caution, of course, is that as we have lots of data points, if we start adding lots of links and connectors, we're going to have a lot more ink on the screen. Right? There's a lot more stuff that has to be visually interpreted. And if we have a large visualization with lots of data points, it can start to get cluttered. That visual complexity starts to make it harder for us to interpret what's going on. And so it's a powerful effect, but it also requires us to draw a lot more stuff. So you need to trade off between what you want to convey and the detriment that you might cause by adding a lot more visual complexity. All right. Related to the connectedness is continuity. And that refers to the fact that our minds naturally interpret smooth shapes more effectively than sharp angles and different kinds of things. Okay, so if you look at this particular chart, right, this is the same network in A and B, just with different drawing styles for the edges. And which one do you find will be more easily interpretable? Most people will say A. Hopefully you agree. And that's because of these curved shapes, the alignment and these sharp angles. As we get into the area where it's crowded, our mind has trouble kind of disconnecting those pieces. Where if you have these nice curving shapes, then it's much easier for us to trace through them. All right? So the implication here is avoid these kinds of sharp discontinuities in your representations. Right? Avoid abrupt changes in your shape. And for example, use curved lines instead of Manhattan-style lines. The problem is Manhattan-style lines, those kind of sharp angles like the streets of Manhattan, are easier for us to algorithmically compute because we can just kind of draw stuff. Go across and go down and you're done. The problem is that they're harder to interpret at times. Okay? So it's a place where we might want to put in effort to make our visualization easier to use. Another concept is symmetry. And when we look at our marks, we often mentally seek balanced, symmetric interpretations of how we see shapes. Okay? So in isolation, when we look at our marks, we think about horizontal and vertical axes to kind of ground ourselves. So in the figure here, on the left, you probably see a square, and on the right, you see a diamond. But those don't exist just in isolation. If we line these up and tilt them, then those larger patterns can define alternative frames of reference. So the line on the left here, you probably see a lot of diamonds all connected to each other, point to point to point to point. Whereas the line on the right, you probably see a line of squares connected to each other, side to side to side to side. But they're all squares that have been rotated, just like you see over there as a clear diamond. Over here, those squares are diamonds, but you see them as squares because they're connected in this long line. So that pattern gives us an alternative frame of reference. So the implication here is add frames of reference to your visualization. Have axes that are well-defined and allow you to interpret things the way you want them to. Okay? Those frames of references will be important for how people perceive. The next concept is the notion of closure, and that's that we tend to perceive things as closed shapes or closed contours. So if you look at A, what you see is a circle and a square overlapping each other. If you look at B, it's the exact same graphical objects, but now we see a square, or a rectangle, and an arc. It's not fully closed, because now we can see what's underneath and we can see that there's a break. But our mind automatically starts to interpret the fact that, or interpolate that circle being closed, even though it's completely covered up. So mentally we try and complete that shape and guess what's behind an including object if things cover each other up. So in our visualizations, we want to be careful of that. Right? We want to make sure that we don't produce occlusions that lead people to false assumptions. Now, often in visualization, if you're just plotting things one on top of the other, you often get this overplotting effect where you have things covering other things up. If you plot one thing first, and then you plot a second thing, and it covers it up, and now all of a sudden, the trend that you're covered up went up, 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 and then fell off at the end. But you covered up with something else that hides that fall off at the end. Well, now the user's not going to perceive that. Right? They're going to assume that that increasing trend continues. So you can hide the insights within your data. So that's a bad part of this. The other part that's good is we can actually embed things kind of in the background, different kind of contours or enclosing shapes to show relationships or sets. And the user will interpret those and interpolate, even though it might be covered up. And we can use that to our advantage to try and provide additional frames of reference and other types of grouping representations. The next one is figure and ground, which is our kind of way of interpreting things such that small objects typically float on top of larger objects. So if you see here in A, we usually see the black objects on top of the white ones, and the white ones on top of the green ones, based largely from their size. In B, we see green objects floating on white, and in C, we see white objects floating on green. Even though it's really the same thing, we just added more green to it. And so that flipped our way of perceiving what is in front and what is behind. And so we need to think of that also when we encode our visual representation. We also often see effects of this in visualization, for example, on a map, where you might be looking at a region and you zoom in and all of a sudden half that region is off the screen and you're just seeing a part of it. So now it becomes hard to see without color coding, maybe in a map, what's land and sea, or what's a building versus a courtyard if you zoom in and you have those kinds of rectangles, because stuff gets cut off and now you start interpreting the smaller things as objects. So I've had a surprise with this in a user study where I designed a visualization, and all of a sudden people started interpreting the negative space. I was drawing visual objects, and people zoomed in, and rather than looking at the shapes that I was drawing, they were looking at the region defined that because I hadn't drawn on it. And they were trying to figure out what meaning those spaces had, and it's this effect that was taking place. So you have to be careful of that and try and overcome those kinds of limitations, or at least be aware. All right, so what else should we consider? We talked about visual variables and these Gestalt laws. We should also be careful to use axes, okay? Help that define our notion of position, the spatial arrangement of our data. That allows us to interpret all the different variables that we've been talking about. Similarly, legends are important. If we're encoding things with size and color, make sure you have legends that tell you what those color maps and sizes mean. What did the different glyphs mean? And then finally, we also want to think about labels. So labels are really powerful if you put them within a visualization, but they're cognitively demanding. You have to read them, a bit like the numbers. Okay? But they'll draw people's attention to look at this label that you put on something. If you look at visualizations that are created for, say, the New York Times or the interactive online journalism websites, right? Often they include a bunch of labels to help you orient yourself initially to what you're looking at. And they just show a couple of key points. There's not a lot of it, it's concise, but it gets you oriented, and then you can dive into the data and start to understand things. So using labels in that way can be really powerful, but make sure they're informative and they're concise, because they will draw users' attention to start reading and can distract from what you're trying to present visually. All right, so we have our visual variables, we have our Gestalt laws, we have the other tips that I just mentioned. All of those give us a set of ground rules. They tell us what we can control, and they tell us what we can perceive, or how they are perceived. And based on those ground rules, we have to come up with that visual representation that helps convey that insight that we're most interested in, and then define that algorithmic mapping to go from our raw data to set those different variables that we talked about, and to set the arrangement of our objects, respecting the Gestalt principles that we talked about, to get a representation that then captures the power of our perception to help us just see the result without having to work for it. And based on those concepts, we can come up with a wide range of really interesting different visual representations. So here are just a few. We'll see a lot more in the next session. These are all different combinations of those same 8 visual variables with things positioned in order to convey specific kinds of insights. And these have all been applied to healthcare data. Now, what we talked about are these foundational concepts. Right? How are we good at comparing size and shape? How are we able to understand color? How do we see patterns across different shapes? That gives us our mental understanding of how people perceive things. That gives us our foundation. On top of that, if we come to a specific visualization problem, we then want to look at the data that we need to visualize. What kind of data do we have? Do we have categorical data? Do we have ordinal data? How many variables do we have? How large is that data? those can help us understand which visual variables make sense and how to use them. Right? If we think about color, if we have a scalar value that is continuous, right, we want to use one kind of color map. If we have categorical value, it's a different kind of color map. And that can tell us how to use those principles in order to make things interpretable. But it's not enough. Right? If someone asks you gives you a bunch of data and says, go create a visualization for this, tell them no. Okay? Because you can't create the right visualization for a data set. There's no such thing, it's undefined. And we saw this in the very beginning. It also requires us to understand what the task is. What are you trying to learn from the data? What are you trying to understand? And it's only by combining your understanding of what data you have, as well as the task that you're trying to solve, that you can build on the fundamental principles that we talked about to come up with a design that's effective for what you're trying to learn.
I would venture to say that you would need a fourth circle, which would be platform.
Yeah, so I'm kind of ignoring the underlying technology. The question was, should there be a fourth circle for a platform, right? Your kind of technology stack. And that's definitely true. That can either limit what you're able to do, or greatly speed you by giving you a bunch of capabilities that are really effective. And that's true. I mean, in a real life system, that's important. You have to design for that. And we'll talk a little bit about some of the technology stack a little later on. But even independent of that, you need to have these two things, right? And then you may be in a position where you can choose a technology stack, and then you can pick one that's effective for what you're trying to do. But if you're constrained within a particular environment, then you're right. If you're stuck in Excel, and what you build has to be in Excel, you have less flexibility than if you're using D3, which is a source code level toolkit that we'll talk about later, where you can kind of build whatever your mind can imagine. Right? So all those things make a big difference. But it's only at the intersection of these three things, where we have data, task, and the fundamental concepts, that we can connect them together and build kind of the right visualization for the right problem that we're trying to solve. So that wraps up my introduction section. I'm happy to answer any questions. We can do that in a minute if people have them. And then we'll move on to our second session. Is there any discussion or comments? Yes, in the back.
Can you comment about using builds effectively, or how they can change the way people look at information?
Can you repeat?
Builds versus animation, not
yes.
Order presentation data.
Yeah, that's right. So yeah, so again, we have to simplify things here for time. Animation is a really interesting topic. There's a lot of work done in looking at how animation can most be used. And the question was about building, right? So how you can build an animation. And often in visualization, we call them staged animations or staged transitions. And those have been shown to be effective. Right? So if you break up all the stuff that's changing into a few different steps, often you can take away things if you're applying a filter, like you're going to a different subset. Some data points may disappear, some may appear, and some other ones might move because they're still around. So if you look at disease prevalence in young people versus old people, right? There might be some diseases that just kind of disappear and other ones that just change their rate. So you can take all the things that disappear first, then animate the things that are still there so you can see how they change, and then introduce the new things that have just arrived, and then mentally you can follow those. So stage transitions have been shown to be effective. It's also true though if you stage too aggressively, where you break it down into too many pieces, the same studies that showed staging is effective actually show a decrease. So it can be more effective than doing everything at once, because if you animate everything, it's hard to follow everything. But if you do too many pieces, then it's also too hard to follow. It becomes this disjoint set of. Any other questions or comments before we move on? Yes?
I think there should be a degree of making a really beautiful presentation with the graphs versus conveying the idea, because the graphs might move you away from the idea too, might drag you into a different, direction. Is there like a good thumb rule for that?
So you're talking about kind of focusing on aesthetics, right? Of how
Correct,
it looks.
correct. For example, if I were to use black and white versus color, I can use really nice stuff with color, and I can throw the listener's mind to a different realm. And
right. Sure. Yeah. So the idea is how much effort should be focused on aesthetics, I guess, and that the aesthetics can distract from the real message. Right? And part of that depends on the use case, I think. If you're creating a magazine and your visualization is designed to try and pull in attention, then focusing on the aesthetic is important, right? Patient engagement is one in the healthcare setting. Or if your goal is to engage people, a really boring, dry chart that just shows the data might not be as effective at engaging somebody into looking at the data, even if it might distract a little bit from the data message. Whereas if it's really an operational setting where someone's using this to fly an airplane, then, or run an ICU, then you might want to focus more dryly on the specific data that has to be seen, because your goal isn't engagement anymore. The person is already fully engaged. Your goal is to help improve decision making, in which case you might want to focus more on just what is useful and less on what is engaging. All right, I'll take one more question, then we're going to pass on, and we'll be available to talk.
About aesthetics, my daughter is a student at Pratt Institute of Design, so I've seen this from a completely different sort of angle. And yet it seems to me that they ought to be combined.
Mm-hmm.
Isn't aesthetics, in fact, one of the design principles that you should be dealing with here?
So I agree. All things being equal, we would love to have a beautiful, wonderful aesthetic, a great design that's engaging and does all the communication. Right? There's no benefit in making something look bad for the sake of looking bad. I think the only tension comes is sometimes you can sacrifice good design principles in terms of being clear at communicating for improving the aesthetic. And that trade-off is something that is worth thinking about depending on the use case. But you're right, we should strive to make engaging good designs even for the really focused, important tasks.
I'm just saying that aesthetics are ultimately an engineering question as well.
Yes, they're important to engineering tasks. It's harder to quantify and measure what that is, but I agree, it's very important. All right, so with that, I'm going to pass the baton over to Jesus, who will talk about our application.